Hello everyone, my name is Seyoung Kim from Samsung Electronics Memory Department, and now I'm in the PhD course of Seoul National University. This work presents a way to isolate the simulation of a large DRAM array by modeling the behavior of the entire array using its active parts only. For a long time, DRAM array simulation is a major bottleneck of the production cycle due to its long simulation time. There have been a lot of researches on the fast DRAM simulator, but there were no suitable ones for transistor level design. The most of circuit designers in the industry still consider the worst case only in practice, which is insufficient for a product requiring low bit error rate. So in this work, recognizing that only one law is active at a time in a DRAM array, we implemented an equivalent array model that can simulate data readout faster within a minute in a conventional SystemVerilog simulator. Here's our proposed methodology to improve DRAM simulation speed. We exploited the regularity of DRAM based on several observations. DRAM is a regular 2D array structure having low cells for data storage. So for any data access, only one row is activated at a time by the word line driver. And the sense data are latched in the binary sense amplifier as shown in the figure. The other inactive cells do not affect the data output. For example, as shown in the figure left, when you want to read the data for row 2, at first we need to activate the word line for row 2. And then we can read that data from the IO line. Similarly, for row 3, the operation is the same, but the output is different because the voltage level in the cell capacitor is different. So based on these observations, we can model the same behavior by using the active circuits only. Figure 2 shows the proposed model. It operates as the steps described here. First, the external C array is initialized as a real value. And then we load a row of values from the C array into the real circuit node. Whenever word line changes, depending on the external commands from the controller. Then we simulate the rest of circuit parts. At the end of the commands activation, we initialize the circuit and repeat the previous steps. As I mentioned before, data timing is the most important characteristic in DRAM verification. Figure 3 describes the circuit operation related to the data access in DRAM cells. Let me explain it briefly to understand DRAM circuit operation related to the command and timing. When the word line level goes high, charge sharing between the pin line and the cell capacitor is triggered. It typically took several nanoseconds. After that period, the sense amplifier enabling signal SAE is generated, and the resulting small deviation of the pin line pair is then amplified by the latch amplifier circuits called the pin line sense amplifier. This procedure is called activation. After this low activation, by selecting column address, we can read data from the IO line as shown in the waveform. These charge sharing and sense amplification operations are purely analog operations. If we can get the analog transfer function from the circuit, we can simulate the behavior in the SystemVerilog simulators. To simulate analog circuit behavior in SystemVerilog, we use XModeler, which is a product of a Science Analog Corporation. It is a fast and efficient event-driven simulator. It can simulate analog circuits in SystemVerilog using the circuit primitives representing analog transfer functions. The circuit we need to model is shown in figure 5. DRAM read path circuits consist of a cell transistor and capacitor, and the core circuits such as a sense amplifier and column selection transistors. Depending on the discrete event triggered by word line signal, the charge sharing and sense amplification process develops the voltage difference of a bin-line pair. After some period, we can read out the data at the output of the I/O sense amplifier. To get the transfer function from the transistor level netlist, we exploit the feature mother gen, which is also one of the products of science analog cooperations. Using it, we can get the equivalent SystemVerilog model of bin-line sense amplifier automatically. The transistor and the circuit elements like a resistor, capacitor, can be converted to the primitives by a piecewise linear model by using a SPICE simulation results, which can be used in SystemVerilog. Here's a resulting converted netlist, and we also check the accuracy compared to the HSPICE simulation. We can see the result shows excellent agreement in terms of voltage and current. From now on, in this section, I'll give you how we implemented the proposed equivalent model of DRAM array in detail. As I mentioned previously, we can make array simulation faster by including its active parts only. We replace the cell array circuits with the external C array. Let me explain the procedures. At first, the primary input for the array model is a word line. Depending on how the word line changes, there are two operations, activation and pre-charge. Because there are a number of word lines connected to array, we need to merge it. Using the OR primitive as in code 1, we generate the effective word line signal for the active row by merging the entire word lines. Let's say this merged signal is a word line cell 0. And then from word line cell 0 to controlling signal, the word line init cell and the word line cell are generated. For controlling active low circuit as in table 2. And then the resulting short pulse word line init cell initializes the cell node voltage level in the circuit netlist. We use the switch primitive to do this. The corresponding cell voltage level is written to V-cell variable. After that, a real cell and a bin-line circuit can operate by a word line cell signal. During word line cell pulse is high, activation operation is performed. The always module for every row can monitor the change of word line by flag act register. Using DPI functions, we can load C array data into SystemVerilog variables. The EXP value here is to compute charge loss due to device leakage during inactive period. We can calculate its exact amount by RC time constant and the exponential functions. The voltage level after charge loss is updated to V-cell 0 for every column. After the low operation is completed, pre-charge command is issued. We need to put the final cell voltage level back to the external array again. By using a built-in sample function, we can get the final voltage after the activation process. We updated this value to C array. This process represents the pre-charge operations. We validated our model by a sequential read test under various array configurations. Varying the number of word lines and bin lines, we observed its scalability in terms of simulation runtime. As you can see in figure 13, under the same number of bin line, increasing the number of word line does not affect runtime. Still, increasing the number of bin line increase number almost linearly. This can be a disadvantage, but the column size usually limited below 1,000 bits in most DRAM. So I guess it will not be a problem. The typical unit size of sub array used in DRAM design is under 512 or 1012 port, which can be easily simulated in our model in several minutes. For low activation, it only took 150 seconds with the full array data. The result shows that speed gain compared to HSpice is over 100 times at the array, which is more distinct under activation and read-all test bench, which activates a row and a read-all column data while increasing column address. Our proposed model is much efficient in this circumstance because most of simulation time is consumed in the activation process. The column access operation does not require any additional internal analog circuit computation in the simulator, so that the runtime improvement seems much better. We also tested the full chip dense array model of 1 gigabit. Each bank having 32 by 12 subarrays. After a bank is activated, 4 and 4 column have been read. We can see analog output depending on the cell data for the row. In this model, we can read 32-bit data for a single row activation. By reading 512 bits, it only took 1,402 seconds with simulating full analog operations. Using the analog to digital converter primitive, we can also get the digital 32-bit data here. I would like to sum up my presentation. We presented a simulation methodology for fast DRAM simulation considering transistor level circuit effects. Our methods can simulate the array equivalently using the active low and the circuits efficiently based on the regularity of DRAM structure and the behavior. It works well with, in the SystemVerilog simulator. The result shows that 100 times faster speed gain compared to HSpice without loss of accuracy. We hope our methodology can be extended to other simulator or algorithm, including DRAM and any memory-like structures. If you have any questions about this, feel free to email me. Thank you for listening.